Got a big fat test coming up. Big fat test coming up. Big fat chemistry test before the final. Yeah! Big fat chemistry test. Big fat chemistry test. Chemistry is such a Oh, hi. Ha! Chemistry is such fun. Chemistry is my bitch. Okay, something like that. That's like, you know, kind of what I want to help you out with today, because I'm going to work a little bit on pH and precipitation. That's where I'm headed, I think. Let's do it. I have a problem that you remember the soluble salts, insoluble salts, maybe earlier on in your chemistry experience, where you tried to figure out, you know, mixing two things together, what's going to happen when you mix them. Is something going to settle out, or is it just going to be happy and mixed together? Well, this is going to be a little bit more mathematical approach to that, and let's see if that gets us where we want to go. So here's what I'm going to do. I've got cobalt hydroxide, something I checked ahead of time that I know is insoluble in water. Transition metals are generally insoluble in hydroxides. And so, when we're talking about salts, right? I looked this one up on Wikipedia, and fountain of knowledge, there it is. 1.0 times 10 to the negative 15th is its solubility product. So we're going to use this in a minute. The question I want to ask is, at what pH could I take a 0.4 molar cobalt 2 plus ion and get a precipitate? Okay, so what pH should I see this cobalt hydroxide start to settle out of a solution given this molarity? This isn't too hard. If you haven't done it before, I'll just walk you through it real quickly. This time, really, I promise. Okay, so let's start out with the reaction. The reaction is just going to be this. The cobalt hydroxide, and the states matter, right? This is going to be an equilibrium reaction. We're starting with a solid because that's what we are concerned with here. And it's going to break up in a solution into cobalt 2 plus ions, aqueous, plus hydroxide ions, also aqueous, but I didn't write it there, but hey, you don't care, right? Okay, so anyway, let's be good about this. I will put it in right now. I will try to put it in right now because this always works so well. Okay, so AQ, not the same color, but that's all right. Okay, so this is my reaction. And what I want to do is say, when can I expect the balance to tip in favor of this side over here, right, to the cobalt hydroxide? So I'm going to take a look at that by way of the solubility product, which we had up above, right? 1.0 times 10 to the negative 15th power, and that is going to be equal to, okay, well, I said it was 0.4 molar cobalt 2 plus ions, okay? And you see the coefficient in this equation is 1, so it's just going to be this concentration plus the concentration of hydroxide ions at the beginning of the reaction. We don't know what they were, but we know that there's a 2 here, so that means we raise this to the second power, and normally we would put a 2 in front of this, but for our purposes we're solving for the absolute concentration of this, so we don't really need to do that right now. So I'm going to solve for the OH concentration, and OH2, or excuse me, OH negative, right? Hydroxide squared is going to be equal to solubility constant over 0.4. So I'm just solving for the OH. And if I take the square root of that, I get the concentration of hydroxide ions. Oh, well, that's better. Okay. Now, if I want the pH from that, well, this is OH, so if I were to just take a negative log of this, I would get the POH, and that's not what I wanted. So I'm just going to say the pH is equal to 14 plus the log of the concentration of my hydroxide ions. And I'm not trying to pull a fast one here. All I'm saying is that 14 minus the POH is going to be this value, and minus and minus is plus. So here we go, solving. I get the pH is equal to 6.7. Okay, that's our equilibrium point. So we're not done yet, but we're really close. All this means is that as soon as I exceed that pH, okay, when pH is greater than 6.7, I gotta stop wiggling the mouse around so much. My wife, she says it drives her crazy. So I'm sorry, I will not do it anymore. I'll try not to. All right, so the KSP here, okay, when it's, well, let's just look at the formula we used up above, okay? Let's think about why the pH getting bigger than 6.7 would make a precipitate form of the cobalt hydroxide. Okay, well, if the let me move down a little bit here. If I were to go up in acid, right, and I were to go down in the base, okay, then what do you expect to see? You expect to see the pH go down, right? The pH will go down because there's more acid than base. Okay. Likewise, if I were to go down in acid and increase in base, then I would see the pH go up. Okay. Now, to look at that in other terms, all I mean is that, first of all, a constant is a constant is a constant. So this is going to stay put when these change, and the value that I get in that reaction is going to determine the direction in which it flows. If Q is greater than KSP, then it's going to flow left. Okay? If it's less than KSP, then it's going to flow to the right. Let's see what that means. Okay? If the reaction is going to the right, that's because we've decreased in pH. That means there's less stuff to react with. It's a product-favored reaction. Okay? What's the product in this case? Well, if we look up at our equation, our product is the cobalt 2+ cation and the hydroxide anions. Okay, so it's product favored, and that means we've got a more acidic solution. Okay, an increase in pH would be the reaction moving leftwards towards the solid, the cobalt hydroxide. Excuse me. So that means there's less stuff to react with. Okay, so we say that the reaction is reactant favored or precipitate favored. It's going to start forming a solid in the solution, and that's all there is to it. That's pH and precipitation. I hope that helps.